Meitnerium. Meitnerium is a synthetic chemical element with symbol Mt and atomic number 109. It is an extremely radioactive synthetic element. The most stable known isotope, Meitnerium-278, has a half-life of 7.6 seconds, although the unconfirmed Meitnerium-282 may have a longer half-life of 67 seconds. The GSI Helmholtz Centre for Heavy Ion Research near Darmstadt, Germany, first created this element in 1982. It is named after Lise Meitner. In the periodic table, Meitnerium is a d-block trans-actinide element. It is a member of the 7th period and is placed in the group 9 elements, although no chemical experiments have yet been carried out to confirm that it behaves as the heavier homologue to iridium in group 9 as the 7th member of the 6D series of transition metals. Meitnerium is calculated to have similar properties to its lighter homologues, cobalt, rhodium, and iridium. Meitnerium was first synthesized on August 29, 1982 by a German research team led by Peter Armbruster and Gottfried Munzenberg at the Institute for Heavy Ion Research in Darmstadt. The team bombarded a target of bismuth-209 with accelerated nuclei of iron-58 and detected a single atom of the isotope Meitnerium-266. This work was confirmed 3 years later at the Joint Institute for Nuclear Research at Dubna. Using Mendeleev's nomenclature for unnamed and undiscovered elements, Meitnerium should be known as EKA iridium. In 1979, during the Transfermium Wars, IUPAC published recommendations according to which the element was to be called unilenium, a systematic element name as a placeholder, until the element was discovered and a permanent name was decided on. Although widely used in the chemical community on all levels, from chemistry classrooms to advanced textbooks, the recommendations were mostly ignored among scientists in the field, who either called it element 109, with the symbol of E109, or even simply 109, or used the proposed name Meitnerium. The naming of Meitnerium was discussed in the element naming controversy regarding the names of elements 104 to 109, but Meitnerium was the only proposal and thus was never disputed. The name Meitnerium was suggested by the GSI team in September 1992 in honor of the Austrian physicist Lise Meitner, a CO discoverer of protactinium, and one of the discoverers of nuclear fission. In 1994 the name was recommended by IUPAC, and was officially adopted in 1997. It is thus the only element named specifically after a non-mythological woman. Meitnerium has no stable or naturally occurring isotopes. Several radioactive isotopes have been synthesized in the laboratory, either by fusing two atoms or by observing the decay of heavier elements. 8 different isotopes of Meitnerium have been reported with atomic masses 266, 268, 270, and 274-278, 2 of which, Meitnerium-268 and Meitnerium-270, have known but unconfirmed metastable states. A 9th isotope with atomic mass 282 is unconfirmed. Most of these decay predominantly through alpha decay, although some undergo spontaneous fission. All Meitnerium isotopes are extremely unstable and radioactive. In general, heavier isotopes are more stable than the lighter. The most stable known Meitnerium isotope, 278Mt, is also the heaviest known. It has a half-life of 7.6 seconds. The unconfirmed 282Mt is even heavier and appears to have a longer half-life of 67 seconds. A metastable nuclear isomer, 270MMT, has been reported to also have a half-life of over a second. The isotopes 276Mt and 274Mt have half-lives of 0.72 and 0.44 seconds respectively. The remaining 4 isotopes have half-lives between 1 and 20 milliseconds. Meitnerium is the 7th member of the 6D series of transition metals. Since element 112 has been shown to be a group 12 metal, it is expected that all the elements from 104 to 111 would continue a 4th transition metal series, with Meitnerium as part of the platinum group metals. Calculations on its ionization potentials in atomic and ionic radii are similar to that of its lighter homologue iridium, thus implying that Meitnerium's basic properties will resemble those of the other group 9 elements, cobalt, rhodium, and iridium. prediction of the probable chemical properties of meitnerium has not received much attention recently. Meitnerium is expected to be a noble metal. Based on the most stable oxidation states of the lighter group 9 elements, the most stable oxidation states of meitnerium are predicted to be the +6, +3, and +1 states, with the +3 state being the most stable in aqueous solutions. In comparison, rhodium and iridium show a maximum oxidation state of +6, while the most stable states are +4 and +3 for iridium and +3 for rhodium. The oxidation state +9, represented only by iridium in plus, might be possible for its congener meitnerium in the nonafluoride and the and cation, although and is expected to be more stable than these meitnerium compounds. The tetrahalides of meitnerium have also been predicted to have similar stabilities to those of iridium, thus also allowing a stable +4 state. It is further expected that the maximum oxidation states of elements from barium to darmstadtium may be stable in the gas phase but not in aqueous solution. Meitnerium is expected to be a solid under normal conditions and assume a face-centered cubic crystal structure, similarly to its lighter congener iridium. It should be a very heavy metal with a density of around 37.4 G/cm3, which would be the second highest of any of the 118 known elements, second only to that predicted for its neighbor hassium. In comparison, the densest known element that has had its density measured, osmium, has a density of only 22.61 G/cm3. This results from meitnerium's high atomic weight, the lanthanide and actinide contractions, and relativistic effects, although production of enough meitnerium to measure this quantity would be impractical, and the sample would quickly decay. Meitnerium is also predicted to be paramagnetic. Theoreticians have predicted the covalent radius of meitnerium to be 6 to 10 pm larger than that of iridium. The atomic radius of meitnerium is expected to be around 128 pm. Meitnerium is the first element on the periodic table whose chemistry has not yet been investigated. Unambiguous determination of the chemical characteristics of meitnerium has yet to have been established due to the short half-lives of meitnerium isotopes and a limited number of likely volatile compounds that could be studied on a very small scale. One of the few meitnerium compounds that are likely to be sufficiently volatile is Meitnerium hexafluoride, as its lighter homologue iridium hexafluoride is volatile above 60 degrees C, and therefore the analogous compound of meitnerium might also be sufficiently volatile. A volatile octafluoride might also be possible. For chemical studies to be carried out on a transactinide, at least 4 atoms must be produced, the half-life of the isotope used must be at least 1 second, and the rate of production must be at least 1 atom per week. Even though the half-life of 278 Mt, the most stable known meitnerium isotope, is 7.6 seconds, long enough to perform chemical studies, another obstacle is the need to increase the rate of production of meitnerium isotopes and allow experiments to carry on for weeks or months so that statistically significant results can be obtained. Separation and detection must be carried out continuously to separate out the meitnerium isotopes and have automated systems experiment on the gas phase and solution chemistry of meitnerium, as the yields for heavier elements are predicted to be smaller than those for lighter elements. Some of the separation techniques used for barium and hassium could be reused. However, the experimental chemistry of meitnerium has not received as much attention as that of the heavier elements from copernicium to livermorium. The Lawrence Berkeley National Laboratory attempted to synthesize the isotope 271Mt in 2002-2003 for a possible chemical investigation of meitnerium because it was expected that it might be more stable than the isotopes around it, as it has 162 neutrons, a magic number for deformed nuclei. Its half-life was predicted to be a few seconds, long enough for a chemical investigation. However, no atoms of 271Mt were detected, and this isotope of meitnerium is currently unknown. An experiment determining the chemical properties of a transactinide would need to compare a compound of that transactinide with analogous compounds of some of its lighter homologues. For example, in the chemical characterization of hassium, hassium tetroxide was compared with the analogous osmium compound, osmium tetroxide. In a preliminary step towards determining the chemical properties of meitnerium, the GSI attempted sublimation of the rhodium compounds rhodium oxide and rhodium chloride. However, macroscopic amounts of the oxide would not sublimate until 1000 degrees C and the chloride would not until 780 degrees C, and then only in the presence of carbon aerosol particles. These temperatures are far too high for such procedures to be used on meitnerium, as most of the current methods used for the investigation of the chemistry of superheavy elements do not work above 500 degrees C. Following the 2014 successful synthesis of seaborgium hexacarbonyl, Sg6, studies were conducted with the stable transition metals of groups 7 through 9, suggesting that carbonyl formation could be extended to further probe the chemistries of the early 6D transition metals from rutherfordium to meitnerium inclusive. Nevertheless, the challenges of low half-lives and difficult production reactions make meitnerium difficult to access for radiochemists, though the isotopes 278Mt and 276Mt are long-lived enough for chemical research and may be produced in the decay chains of 294Ts and 288Mc respectively. 276Mt is likely more suitable, since producing Tenney's sign requires a rare and rather short-lived berkelium target.